Good day, Grade 8 learners! Welcome to our Mathematics Quarter 1, Module 5, Systems of Linear Equations into Variables and Their Graphs, Week 8. In learning this module, you have to prepare the following: a notebook and a pen to take note of important points during the discussion. Are you now ready? Now let's proceed. This module is divided into two lessons. Lesson 1, Systems of Linear Equations in Two Variables and Their Graphs. Lesson 2, Kinds of Systems of Linear Equations in Two Variables. After going through this module, you are expected to illustrate systems of linear equations in two variables, graph a system of linear equations in two variables, and categorize when a given system of linear equations in two variables has graphs that are called parallel, intersecting, and coinciding. Before we proceed to the discussion, let's find out first if you have pre-existing knowledge about the lessons in this module. What I know. Instructions: choose the letter of the correct answer. Write your chosen answer on a separate sheet of paper. So you have here 1 to 15 items. And take note, you have to answer letters only. Now let's start the discussion. Lesson 1, Systems of Linear Equations in Two Variables and Their Graphs. What I need to know. At the end of the lesson, you are expected to describe and illustrate systems of linear equations in two variables and graph a system of linear equations in two variables. What's in? Let us recall on graphing linear equations in two variables. Let us try to draw the graph of each of the following linear equations in a Cartesian plane and give your own idea on the following questions that follow. So we have here the equation y is equal to 3x plus 2, where m is equal to 3 and b is equal to 2. So we know that m stands for the slope and b stands for the y-intercept. So the first step that we are going to do is to plot the coordinates of the y-intercept, which is 0, 2. So how did we get the coordinate 0, 2? So we let x is equal to 0 to the equation y is equal to 3x plus 2. So substitute 0 to x. So we have here y is equal to 3 times 0 plus 2. So y is equal to 2. So the coordinate is 0, 2. And this time we're going to plot this in the Cartesian plane. So we have here. And now we're going to plot another point using the slope. So we know that our slope is equal to rise over run, or we simply write as 3 as our rise and 1 as our run. So from the point of the y-intercept, so we have to move 3 steps upward since our rise is positive. So 1, 2, 3, and we have to run 1 step to the right since 1 is also positive. So we are going to plot the point here. So we have the coordinate 1, 5, and this is the graph of the equation y is equal to 3x plus 2. So now let's have our second equation, 2x plus y is equal 5, where our slope is equal to negative 2 and our y-intercept is equal to positive 5. So same as what we did in number 1, we are going to plot first the coordinate of our y-intercept. So our y-intercept is 5. What is the coordinate of this? Right, it is 0, 5. So on the Cartesian plane, we're going to have 0, 5. 0 as our x and 5 as our y. So we're going to plot 0, 5. So after plotting the y-intercept, what are we going to do next? Yes, plot the coordinates based on the slope, which is negative 2. Since our slope is negative, what are we going to do? We still have to follow the rise over run. That's correct. So we have to move 2 units upward from the coordinate of the y-intercept. So it's 2 units. And since it is negative, we need to move 1 unit to the left. So our coordinate is negative 1, 7. So is this the only way of plotting the coordinates of the slope if it is negative? Right. We still have another way. You can also do this. So from the coordinate of the y-intercept 0, 5, so we just have to move 2 units downward because the slope is negative. So 2 units downward, so from 5, we're going to go to 3. And the run will be positive. So because we already made the rise as negative. So 2 units downward, so we are here 3 and 1 unit to the right. So we have here the coordinate 1, 3. So this is the line, or this is the graph of the equation 2x plus y is equal to 5. Did you get it? I believe so. So how did you graph each linear equation into variables? How do you describe the graphs of linear equations into variables? So in the next slides, you will be able to find out. And yes, let's find it out together. What's new? What if the graphs of 2 or more linear equations in 2 variables are drawn in the same Cartesian plane? How will you describe the graphs? So let's see the following examples. So we have here example 1, y is equal to negative x plus 7 and y is equal to 2x plus 1, where in equation y is equal to negative x plus 7, the slope is equal to negative 1 and the y-intercept is equal to 7. For the equation y is equal to 2x plus 1, the slope is positive 2 and the y-intercept is positive 1. So applying the same principle in our review a while ago, we're going to plot the equations y is equal to negative x plus 7 and y is equal to 2x plus 1 using the slope and y-intercept on the same Cartesian coordinate plane. So we're gonna start first with y is equal to negative x plus 7, in which the y-intercept is 7, so the coordinate is 0, 7. So we're going to plot 0, 7. So we have here, and since our slope is negative 1, so we need to go down 1 unit downward and 1 unit to the right. So we have here the graph of the equation y is equal to negative x plus 7. So now, we're going to plot the equation y is equal to 2x plus 1. And the y-intercept is 1. So, our coordinate for this is 0, 1. So, let's plot 0, 1 here. And the slope is positive 2. So, we need to move upward 2 units. 1, 2, and then 1 unit to the right. So we have here the coordinate. And this is the graph for the equation y is equal to 2x plus 1. Do you think it was easy? Now let's have another example. Let's have example 2. Y is equal to 5x minus 2 and y is equal to 5x plus 3. So for the equation y is equal to 5x minus 2, what do you think is the slope? Yes, it's positive 5. How about the y-intercept? Alright, it's correct. It's negative 2. So for equation y is equal to 5x plus 3, what do you think is the slope? Yes, it's positive 5. How about the y-intercept? This time, yes, it is positive 3. So as you noticed, they have the same slope. We already have the slope and the y-intercept of both equations. So now, let's plot each of the equation. Let's start first with y is equal to 5x minus 2. So, you have here the y-intercept, which is negative 2. What is the coordinate? Yes, it is 0, negative 2. So let's plot and let's find a point on the Cartesian plane, 0, negative 2. So we have here down to the negative y. So this is where we plot 0, negative 2. And since the slope is positive 5, what are we going to do? Right, we have to move 5 units upward and 1 unit to the right because it's positive. Very good. So let's move 1, 2, 3, 4, 5 and 1 unit to the right. So we have here the coordinate 1 and positive 3. So this is the graph of the equation y is equal to 5x minus 2. This time, we're going to plot the equation y is equal to 5x plus 3. So you already know the coordinate of this y-intercept 3. And what is it? Yes, it's 0, 3. So since it's positive, so we're going upward. So 3 units. So it's 0, 3. And the slope is positive 5. So we're going how many units upward? Right, it's 5 units. So 1, 2, 3, 4, 5. And we are now on the point 8. So, and going to the right because it's positive. So we have here the point. So our coordinate in this case is positive 1 and positive 8. So this is the graph of the equation y is equal to 5x plus 3. Have you already noticed what kind of graph did example 1 and example 2 formed? Would you like to have another example? Since it's a yes, let's have example 3. Y is equal to 3x plus 6 and 2y is equal to 6x plus 12. So we have the first equation, y is equal to 3x plus 6. What is the slope on the y-intercept? Yes, the slope is equal to 3 and the y-intercept is equal to 6. So how about the equation 2y is equal to 6x plus 12? What could be the slope and the y-intercept? So as you can see, the numerical coefficient of y is 2. And take note, in the slope-intercept form, it should be y is equal to mx plus b, wherein the numerical coefficient of y must be equal to 1. So in this case, since the numerical coefficient of y is 2, and as you can see, for the numerical coefficient of x, it's 6 and the constant is 12, we can divide both sides by 2. So, in order to get the slope-intercept form y equals mx plus b, let's divide both sides by 2, so it will now become y equals 3x plus 6, wherein our slope is equal to 3 and our y-intercept is equal to 6. And as you can see, both equations have the same slope and the same y-intercept. So what could be the graph? Now let's plot y is equal to 3x plus 6 on the Cartesian plane. So we have here our y-intercept, which is 6. So our coordinate is 0, 6. So let's plot it here. And the slope is 3, so we need to move 3 units upward and 1 unit to the right since it's positive. So 1, 2, 3. So we have here 9, and to the right we have 1. So this is the graph of the equation y is equal to 3x plus 6. So how about 2y is equal to 6x plus 12? So again, we have the y-intercept 6, so the coordinate is also 0, 6. And since the slope is also 3 and it's positive, so the coordinate is also 1, 9. And this is the graph of 2y is equal to 6x plus 12. So what can you say about their graphs? I hope you were able to catch up and understand the 3 examples. Now, what have you observed in each of the graph? Now, let's practice more. Activity 1, draw me. Directions, determine the slopes and y-intercepts in each system. Then draw the graph of each pair of linear equations using the same Cartesian plane. Kindly use a separate graphing paper in sketching the graph. So all you have to do is just to follow what we have done a while ago. So these are the equations. For number 1, y is equal to negative 3x plus 4 and y is equal to 3x minus 2. For number 2, y is equal to 5x plus 4 and negative 5x plus y is equal to negative 2. Number 3, you have 3y is equal to x plus 5 and negative 2x plus 6y equals 10. So, find the slope and y-intercept, then draw the graph on the same Cartesian plane. Good luck! I know you can do it. I hope you got the correct answers in the activity 1. Now, let us dig and discover more about this topic. Focus in each pair of linear equations in activity 1 and try to give some observations. Try to answer the following questions on your own idea. Number 1. Which pair of equations has graphs that are intersecting? How many points of intersections do the graphs have? What are the coordinates of their points of intersection? Number 2. Which pair of equations has graphs that are not intersecting? Why? What is it? So going back to what you have answered in activity 1, what do you call the pairs of linear equations that you have answered? Alright, that's it. Very good. Those pairs of linear equations are called simultaneous linear equations, or we also call it systems of linear equations. So what do you mean when we say systems of linear equations? Alright? It means that it is a set or collection of linear equations, all of which must be satisfied. So it can be written with ax plus by is equal to c and dx plus ey is equal to f. So this symbol here corresponds a system. So in which where a, b, c, d, e, and f are all real numbers and the coefficients of x and y are not both 0 for each equation. And take note that the point of intersection of the graphs of two linear equations is called the solution of the system. So, when talking about linear equations in two variables, the solution set of an equation is an ordered pair of numbers that satisfies both equations. And the solution set of a system of linear equations in two variables is the set of all ordered pairs of real numbers that makes every equation in the system true. The solution of the system of linear equations can be determined algebraically or graphically. And to find the solutions graphically, graph both equations on a Cartesian plane, then find the point of intersection of the graphs, if it exists. The solution to a system of linear equations corresponds to the coordinates of the points of intersection of the graphs of the equation. Better look at this. Determine how many solutions does each pair of equations have. Let's graph each system of linear equations in one Cartesian plane to check if the number of solutions in each system of linear equations is correct. And after that, we're gonna describe the graph of each system. So as you can see, the first pair has exactly one solution. The second pair has no solution. The third pair has infinitely many solutions. So let's find out if this number of solutions are correct. Now let's have the first pair of linear equations, or the system of linear equations. We have here y is equal to negative 3x plus 4 and y is equal to 3x minus 2. And let's find out if it has exactly one solution. So applying what we have learned in graphing systems of linear equation, let's graph first y is equal to negative 3x plus 4. So in this case, we know that our slope is, alright, it's negative 3. And our y-intercept is, right, it's positive 4. So let's plot first the coordinate of our y-intercept, which is 0, 4. So we have here 0, 4. And since the slope is negative, so it's negative 3, so we have to go down 3 units downward and 1 unit to the right. 1, 2, 3, and then 1 unit to the right. So we have here the coordinate 1, 1. So the first graph of the equation y is equal to 3x plus 4 is here. Now let's graph y is equal to 3x minus 2. So the slope is, alright, it is positive 3. And the y-intercept is, what is it? Yes, it's negative 2. And let's plot. So we have here the coordinate 0, negative 2. And since the slope is positive, what are we going to do? Remember? Yes, we have to go up 3 units upward from the coordinate of the y-intercept. So 1, 2, 3, and 1 unit to the right. So we have here 1, 1. And this is the graph of y is equal to 3x minus 2. And as you can see, based on the graph of the two equations, the graphs are, or the lines are, intersecting to a common point, which is 1, 1. So with this, it is correct that these two equations, or this system of linear equation, has exactly one solution. Did you get it? Alright, that's good to know. Now, let's have the second pair of the system of linear equations. Y is equal to 5x plus 4 and negative 5x plus y is equal to negative 2. It states here that it has no solution. So let's check if it really has no solution. Alright, so let's have the first equation, y is equal to 5x plus 4. And we know that the slope is, alright, it's positive 5. And the y-intercept is, Right, it's positive 4. And the coordinate of the y-intercept is 0, 4. And here we're going to plot 0, 4 on the Cartesian plane. And now let's plot another point using the slope. So we have here positive 5. Therefore, we're going to move downward or upward. Right, it is upward since it's positive slope. So we're going to move 5 units from the coordinate of the y-intercept. 1, 2, 3, 4, 5, and then move 1 unit to the right because it's positive. So our second point is 1, 9. And this is the graph of our equation y is equal to 5x plus 4. Now, we're going to have negative 5x plus y is equal to negative 2. As you can see, it is not in the slope-intercept form, y is equal to mx plus b. So in this case, we're going to rearrange this equation. And how are we going to do it? Alright, so all we have to do is to cancel negative 5x here on the left side and move it to the right side. So, in order to do it, we're going to add both sides by positive 5x to cancel negative 5x here at the left side, and this is in accordance to the additive inverse. Alright, so here we can already cancel out 5x minus 5x, so the remaining equation or the new equation will now become y is equal to 5x minus 2. With this, we can already find out the slope and the y-intercept. So in this equation, what is the slope? Alright, it is 5. And the y-intercept? Alright, it is negative 2. So as you can see, both equations have the same slope. And let's find out if they will intersect to each other. So let's plot first the coordinate of the y-intercept negative 2, and that is 0, negative 2. And since the slope is positive, so let's move 5 units upward from this point. 1, 2, 3, 4, 5, and 1 unit to the right. So we're gonna have the point here with the coordinate 1, 3. And this is the graph of the equation negative 5x plus y is equal to negative 2. So what can you say about the graph? Right, the lines are parallel to each other. And since there are no points that intersect, so these lines did not intersect to each other, therefore, this system of linear equation has no solution, and it is correct. Now, let's have the last pair of the system of linear equations. 3y is equal to x plus 5 and negative 2x plus 6y is equal to 10. It states here that it has infinitely many solutions. And let's check why. So now, let's plot first 3y is equal to x plus 5. But as you can see, y here has the numerical coefficient of 3. And take note that the slope-intercept form has the form of y is equal to mx plus b, wherein y has a numerical coefficient of 1. So in order to follow the y equals mx plus b form, we have to divide both sides by positive 3 to cancel 3 on the left side. So the new equation will now become y is equal to x over 3 plus 5 over 3, where our slope is equal to 1 over 3 and our y-intercept is equal to 5 over 3. And this time, we can already plot the points on the Cartesian plane. So let's start with the y-intercept coordinates. So we are going to have 0, 5, 3. So here's the point. And then since our slope is 1 over 3 and we all know that 1 here corresponds to the rise and 3 here is the run. So we're going to move 1 point upward and 3 units to the right. So we are going to have the point here. And this is the graph of our equation 3y is equal to x plus 5. Now let's have the second equation. Negative 2x plus 6y is equal to 10. As you can see, it is in the standard form ax plus by is equal to c, and we need to transform this one into y is equal to mx plus b. In order to do that, we have to add both sides by positive 2x to cancel the 2x here at the left side. So our new equation will now become 6y is equal to 10 plus 2x. And since y here has the numerical coefficient of 6, so we still have to make it into 1. So in this case, we have to divide both sides by positive 6 in order to cancel the 6 at the left side. So the new equation will now become y is equal to x over 3 plus 5 over 3. And as you can see, the slope and the y-intercept in the first equation and the second equation are all the same. So we have the slope 1 over 3 and b, or the y-intercept, which is equal to 5 over 3. Therefore, the line coincides to each other. And since the line coincides to each other, then it has infinitely many solutions. So we can have here the solutions, the points. So that's why it is called infinitely many solutions. I believe this part is clear. Based on the discussion, we can conclude that a system of linear equations has only one solution if their graphs intersect at only one point, no solution if their graphs do not intersect, and has infinitely many solutions if their graphs coincide to each other. So that's it on the systems of linear equations in two variables under graphs. This time, it's now your turn. What's more, activity 2. Determine the number of solutions of the system of linear equations by graphing. Then describe whether the lines are intersecting, parallel, or coinciding. Use a separate graphing paper in sketching the graph. So we have here 3 columns. So the first column is all about the systems of linear equations. The second column is all about the number of solutions. So you are going to write here how many number of solutions does each system have. And on the third column, you're going to describe here what kind of lines as you graph the system on the Cartesian plane. So we have here number 1, 4x plus y is equal to 2 and x minus y is equal to 3. Number 2, we have here negative x plus 3y is equal to negative 6. And 6y is equal to 2x plus 6. Number 3, we have y is equal to negative 2/3 x minus 1 and negative 4x minus 6y is equal to 6. Number 4, we have 4x plus 2y equals 10 and x minus y is equal to 13. And number 5, x plus 4y is equal to 1 and y is equal to negative 1/4 x plus 2. Good luck! I know you can do it. And here are the key points that you have to remember in this lesson. What I need to remember: first, the system of linear equations is a set or collection of linear equations, all of which must be satisfied. It can be written ax plus by is equal to c and dx plus ey is equal to f, where a, b, c, d, e, and f are all real numbers and the coefficients of x and y are not both 0 for each equation. Second, you have to remember that the solution of the system is the point of intersection of the graphs of two linear equations. It is an ordered pair of numbers that satisfies both equations. And the last thing that you should not forget is that a system of linear equations has only one solution if their graphs intersect at only one point. It has no solution if their graphs do not intersect, and it has infinitely many solutions if their graphs coincide to each other. Once again, remember those key points. In Lesson 1, you'll learn about the different systems of linear equations in two variables under graphs. And this time, let's add more information in your existing knowledge. Are you now ready? Alright, let's discuss about Lesson 2, kinds of systems of linear equations in two variables. What I need to know. At the end of the lesson, you are expected to categorize when a given system of linear equations in two variables has graphs that are parallel, intersecting, and coinciding. And determine the kind of systems of linear equations in two variables. This time, let's have a review. What's in? Remember that the characteristics of the graphs of the system in the same Cartesian plane can be used to determine the number of solutions a system has. More so, the characteristics of the system can also be used to categorize according to its kinds. As you can see in this graph, the lines are intersecting, so therefore, it has exactly one solution. In the second graph, the lines are parallel and so it has no solution. And for the third graph, since the lines are coinciding, then therefore, they have infinitely many solutions. What's new? Given these three systems of linear equations listed, can we determine the number of solutions right away? No, right? We can only do that by graphing the system in one Cartesian plane. And let's graph them based on our knowledge in the previous lesson or modules. Now let's graph the system x plus y is equal to 2 and 2x plus y is equal to 1. And as you can see, they are in standard form and we need to change this one into slope-intercept form. So take note, the slope-intercept form is in the form of y is equal to mx plus b, and we need to determine the slope and the y-intercept to graph here on the Cartesian plane. So let's start with x plus y is equal to 2. In order to transfer the x to the left side, we need to add both sides by the additive inverse of positive x, in which the additive inverse of positive x is negative x. So, in this case, we can already cancel out x on the left side, and we have here y is equal to negative x plus 2, where m is equal to negative 1, and our y-intercept is equal to 2. And for the equation 2x plus y is equal to 1, we just have to do the same principle, add the additive inverse of positive 2x, which is negative 2x to both sides, to cancel the 2x on the left side. So we will be able to have the equation y is equal to negative 2x plus 1, where our slope is equal to negative 2 and the y-intercept is equal to 1. And after this, we're going to plot in the Cartesian plane using the slope and y-intercept. And based on the previous lesson and previous module, you know that in getting the coordinate of the y-intercept, all we have to do is to let x is equal to 0 to the first equation x plus y is equal to 2 and substitute 0 to x, so we will have y is equal to 2 or 0, 2. So let's plot 0, 2 on the Cartesian plane, and then based on our slope, we have here negative 1, so we need to go down 1 unit downward and 1 unit to the right. So we're going to plot it here, and this is the graph of the equation x plus y is equal to 2. This time, let's graph 2x plus y is equal to 1, wherein the y-intercept is 1, so the coordinate is 0, 1. So here's the coordinate here, and the slope is negative 2, so we need to go down 2 units from the point of the slope, from the point of the intercept, and then 1 unit to the right. So here we are going to plot the point. So this is the graph of our equation 2x plus y is equal to 1. And as you can see, the lines are intersecting. Since the lines are intersecting, therefore they have a common point which has the coordinate of -1 and 3. Based on the graph, we can conclude that this system has one solution. Now, let's have the second system. 3x minus y is equal to 4 and y is equal to 3x plus 2. So just the same as before or the other examples a while ago, we are going to change the equations to slope-intercept form y equals mx plus b to determine the slope and y-intercept. So based on the equation, which of these two are we going to change into y equals mx plus b? Is it the first or the second equation? Alright, yes, it's the first equation since the first equation is in standard form. So how are we going to do it? So we have here 3x minus y is equal to 4. So in order to change it to the slope-intercept form, we're going to add the additive inverse of 3x to both sides to cancel 3x at the left side and move it at the right side. So we have here 3x plus negative 3x minus y is equal to 4 minus 3x. So we can cancel 3x minus 3x, so we can have y is equal to negative 3x plus 4. And since our slope-intercept form states that our y should be positive, so in this case, in this equation, our y is negative. How are we going to make it positive? Can you think of how can we do it? Alright, yes, that's correct. We have to multiply both sides by negative or a -1. So multiply negative times negative, y is equal to positive y, and negative multiplied by a negative 3x, it's positive 3x, and negative multiplied by positive 4, it will now become negative 4. So our new equation will be y is equal to 3x minus 4, and our slope will be positive 3, and the y-intercept is negative 4. So for y is equal to 3x plus 2, all we have to do is just to directly get the slope and the y-intercept, which is m is equal to 3 and b, or the y-intercept, is equal to 2. The next step is to plot those points using the slope and the y-intercept in the Cartesian plane. So let's start first with 3x minus y is equal to 4. So we were able to get the y-intercept, which is negative 4. So what is the coordinate of this y-intercept negative 4? Yes, it is 0, negative 4. And here it is. And since the slope is positive 3, what are we going to do? Do you still remember? Alright, yes, we have to move 3 units upward and 1 unit to the right. So here is the point, and this is the graph of the equation 3x minus y is equal to 4. Now let's graph the equation y is equal to 3x plus 2. The y-intercept is 2, and so the coordinate is 0, 2. So we are going to plot here. And the slope is positive 3, so we have to move again 3 units upward and 1 unit to the right. And this is the graph of the equation y is equal to 3x plus 2. So what can you say about the lines of this system? Alright, yes. So as you can see, the lines are parallel. So therefore, there is no solution in this system. Now let's have the third systems of the linear equations in two variables, x plus 3y equals 6 and 2x plus 6y is equal to 12. So just like the first and the second systems, all we have to do is to change the equations to slope-intercept form to determine the slope and y-intercept. So based on our given system, so which of these equations are we going to change into slope-intercept form? Alright, is it the first or the second equation? Okay, you're right. It's both equation because both of them are in standard form ax plus by equals c. So let's start first with x plus 3y equals 6. So all we have to do is to add both sides by the additive inverse of positive x so that we can transfer x to the right side. And we can cancel x at the left side. So we can have here 3y is equal to negative x plus 6. And since, as you all know, we need to divide both sides by 3 so that we can just have y equals mx plus b. So divide both sides by 3 and you will have the equation y is equal to negative 1/3 x plus 2, in which our slope is negative 1/3 and our y-intercept is positive 2. Now let's have the second equation, 2x plus 6y is equal to 12. So just like the first equation, we're going to add both sides by the additive inverse of 2x so that we can cancel it at the left side and transfer it to the right side. So we will have 2x plus negative 2x plus 6y is equal to negative 2x plus 12. And your equation will now become 6y is equal to negative 2x plus 12. And let's divide both sides by 6 so that we can cancel 6 and we will have the form y equals mx plus b. So the answer would be y is equal to negative 1/3 x plus 2, wherein our slope is equal to negative 1/3 and our y-intercept is equal to positive 2. And the next step is to plot the points in the Cartesian plane using the slope and y-intercept. So let's plot first the first equation, x plus 3y equals 6. And we will have here 0, 2, since our y-intercept is 2. So the coordinate is 0, 2. And since our slope is negative 1/3, so we're going to move 1 point or 1 unit downward and move 3 units to the right for the run. So we have here the graph of x plus 3y equals 6. Now let's graph the equation 2x plus 6y is equal to 12. Since as you can see, the first equation and the second equation have the same slope and y-intercept, therefore they just have the same line. And as you can see, the lines are coinciding. So with this system has infinite many solutions. Here's the graph of the three systems that we answered a while ago. So how would you compare the slopes of the lines defined by the linear equations in each system? So what can you say about their slopes? Do they have the same slopes? How about their y-intercepts? What can you say about each of their slope and y-intercept? Do they vary? Are they the same or what? So what systems can you make about the solution of the system in relation to the slopes of the line? So as you can see, by mere inspection of the constants in the system of linear equations, you can easily tell what kind of system it is and how many solutions it has, if any. So based on their slope and y-intercept. So let's find out how. What is it? There are three kinds of systems of linear equations in two variables according to their number of solutions. These are, we have here number 1, system of consistent and dependent equations. So in this system of linear equations, it has infinitely many solutions. The slopes of the line defined by the equations are equal and their y-intercepts are also equal. Their graphs are also coinciding. So let's go back to the system of equations. X plus 3y is equal to 6 and 2x plus 6y is equal to 12. So the system here is consistent and dependent. So as you can see, the slopes are equal. Their y-intercepts are also equal and the graphs coincide to each other. The second kind of system of linear equation is system of inconsistent equations. So in this system, it has no solution. The slopes of the lines defined by the equations are equal. Their y-intercepts are not equal, and their graphs are parallel. So let's look at this example. We have here the example 3x minus y is equal to 4 and y is equal to 3x plus 2. And this is the graph of the system. So the system is inconsistent. The slope is equal as you can see. But their y-intercepts are not equal. And the graphs of this system is parallel. So this is the second kind of system of linear equations in two variables. Now let's have the third kind of system. So this system of linear equations is called system of consistent and independent equations. It has exactly one solution. The slopes of the lines defined by the equations are not equal, and also their y-intercepts could be equal or unequal. Take note of that. And their graphs intersect to each other. The example of this system is this equation, x plus y is equal to 2 and 2x plus y is equal to 1. So as you can see, the system is consistent and independent to each other. So the slope is not equal, the y-intercepts are not equal, and the graphs are intersecting. So the lines are intersecting to each other. And those are the three kinds of systems of linear equations in two variables. Take note, we can also determine the kinds or classification of the systems of linear equations in two variables by looking at the ratio of their constants. So let's look at the table here. So we have the systems of linear equations in two variables written in a sub 1 x plus b sub 1 y is equal to c sub 1 and a sub 2 x plus b sub 2 y is equal to c sub 2. So we can say that the lines are intersecting if a sub 1 over a sub 2 is not equal to b sub 1 over b sub 2. The graph of the lines are parallel if a sub 1 over a sub 2 is equal to b sub 1 over b sub 2 but not equal to c sub 1 over c sub 2. So in this case, we can say that the system is inconsistent. So the first one was the system is consistent. For the third one, we can say that the lines are coinciding and the system is consistent if a sub 1 over a sub 2 is equal to b sub 1 over b sub 2 is not equal to c sub 1 over c sub 2. I believe you already got the information that you need to know from lesson 2. And now it's your turn. What's more, activity 3, tell whether each statement is true or false. We have here 5 items. Number 1, the graphs of dependent equations are the same. Number 2, the system of equations y is equal to 5x plus 2 and y is equal to 5x plus 3 is inconsistent. Number 3, the system of equations y is equal to x minus 3 and y is equal to 2x plus 2 is independent. Number 4, the graphs of dependent linear equations intersect at exactly one point. And number 5, if two equations of a system are equivalent, the equations are dependent. So we have another activity under activity 3, letter B. Fill in the blank with the correct term of phrase. And we have letter C, identify whether the system is consistent or inconsistent. If the system is consistent, state whether the equations are dependent or independent. State whether the system has exactly one solution, no solution, or infinitely many solutions. So these are the items. These are the different systems of linear equations in two variables. I know you can do it, everyone. Good luck! So here are the different takeaways that you need to take note from lesson 2. What I need to remember. Don't forget that by mere inspection of the constants in a system of linear equations, you can easily tell what kind of system it is and how many solutions it has, if any. There are three kinds of systems of linear equations in two variables according to their number of solutions, and these are system of consistent and dependent equations. This is a system of linear equations having infinitely many solutions. The slopes of the lines defined by the equations are equal, their y-intercepts are also equal, and their graphs coincide. Number 2, system of inconsistent equations. This is a system of linear equations having no solution. The slopes of the lines defined by the equations are equal, their y-intercepts are not equal, and their graphs are parallel. We have the last one, system of consistent and independent equations. This is a system of linear equations having exactly one solution. The slopes of the lines defined by the equations are not equal. Their y-intercepts could be equal or unequal, and their graphs intersect. So take note of those. So here's your performance task for this module. What I can do. Activity 4, what is the exact location of the treasure? The materials that you're going to need are the following: graphing paper, pencil, ball pen, and ruler. Coloring material is optional. So here's the situation. Lucas and Jerry wanted to locate the treasure left by their rich friend. The treasure is in the island where both are living. Both of them will only follow a straight line from their houses. The treasure is hidden in the location which both of them meet. Lucas will follow the line which has an equation of x plus y is equal to 6, while Jerry will follow the line which has an equation of x minus 3y is equal to negative 2. Replicate the treasure island on the graphing paper and locate the exact location of the treasure by encircling the exact point where they meet. Describe the location of the treasure. So this is the treasure island. So break a leg in this performance task of yours, everyone. And now we are already on the last part of the module in which you're going to sum up all of your learnings and check your understanding through this assessment. So just like what I know, here is the instructions. Choose the letter of the correct answer. Write your chosen answer on a separate sheet of paper. So there are also 15 items here. And all you have to do is to write letters only on a separate sheet of paper. And I know you will get a good score in this part. You can also refer to your module on pages 13 to 14. Let me end this module with a quotation from Koshan Wisdom: the harder you work for something, the greater you'll feel when you finally achieve it. And I believe that as you work on with the activities in this module, you will feel rewarded as you answered all the activities on your own honestly. And that's all for this module, and I hope you learned from it. See you next time.